Okay, thank you for coming to the seminar today, everyone. We're very excited to announce Jerry, who is a research fellow at the Oxford Mann Institute at the University of Oxford. He is an expert in filtering, Bayesian inference and post-Bayesian inference, and we're very excited for his talk today on learning and adapting in non-stationary environments. Jerry,
thank you. Thank you so much for the invitation. Very excited to be here and present this work. Now, the purpose of this talk is to give you a bit of an overview of this framework that we've been working on called BONE. It stands for Generalized, Bayesian, and Non-Stationary Environments. But I wanted to give a bit of an overview of what this framework is in a bit of a tutorial way to hopefully just hopefully the idea stick a bit better than previous past that I presented it. So what I'm going to do is present the framework. I'm going to introduce some examples. As we go along, it's going to make sense why we do each of the steps. And yeah, so I'll be talking about this. Now, this joint work with my colleagues, Leandro Sanchez from Oxford, Alex from Queen Mary, Kevin from Google, and some of the colleagues, again, from the OMI, Alvaro Cartea, Gianluca Palmari, Faisal Tracy, and ForestU, which have worked on some follow-up papers from the framework that I'm going to be presenting. Great. So this talk is really about non-stationarity, and I talk about non-stationarity in a very vague way. I mean, you can hear this term from classical literature, but as well as in the machine learning literature, and it can be something either very precise, as in like in the time series literature, where you have the concept of weak and strong non-stationarity. But it can be also a bit vague, as in the machine learning literature, where there's a concept of non-stationarity that is very practical in terms of a loss function or in terms of something that you want to minimize. So, sorry, I'm just gonna mute it all. So from the from the classical literature, we can have the statistics literature. You can have concepts like changepoint detection methods, such as like the product partition model, which assumes that data generating process comes in a batch of data points, and every data point within this batch or within this time span follows an IID distribution. There's also non-stationarity in signal processing, for instance, in adaptive filtering methods, where you assume some sort of state space model. But because the state space model is specified, then you want to adapt to that, the non-stationarity or the state space being changing by some artifact-sharing model. There's also in the economics, you can find the hints of non-stationarity, talking about economic cycles or regime, if there's a boom or a bust, or high volatility and low volatility. And also, as I said, the time series forecasting, where you can talk about weak and strong non-stationarity. But then in recent years, there's also been a push in the machine learning literature to tackle the problem of non-stationarity. For instance, you can find it in the online continual learning problem, which the idea, again, not very well defined, but is that you have this model, you have some fixed data set, and this data set changes over time, whatever that is. Typically comes from a different data set from healthcare or finance or every other task, and you want this model that performs well as you go along. And there you can experience these problems of context drift, catastrophic forgetting, or replay buffers. You also have in the meta learning, you also see this problem of non-stationarity popping up there, as well as in reinforcement learning literature, where you have these agents, but the agent may not be complex enough to really capture the environment that it's in, so you want to adapt to the environment. So really the motivation behind the paper that we worked on is that if you look at the machine learning literature, many of the times the methods that they create can be seen or derived from the classical literature. And sometimes they don't recognize that either because the machine learning literature is big on its own, or simply because they didn't care or didn't think that the classical literature could be used in the machine learning literature. So sometimes when you look at the machine learning literature, a new method is proposed, a new data set is proposed, a new metric, and you want to minimize the loss, you show that your new method is the best, and that's it. But if you really dissect what really they're doing to what the classical literature is doing from an algorithmic perspective, you can start to see that there are some patterns there that we can mix and match. So really the point of the paper is to, well, how do we think about the general concept of modeling non-stationarity from an algorithmic point of view? How do we construct these methods? How do we adapt these methods? What even means a regime? So that if we propose a new method or want to compare a different method, we have like different pieces of the puzzle that we can compare systematically. So having said that, the framework that we put forth is the BONE framework, which stands for Bayesian online learning in non-stationary environments. And really the idea is to adapt and learn in these non-stationary environments, but the point is to have maximum predictive performance. You can care about interpretability. In our framework, we really care about predictive performance, but again, because we really try to put together different methods in the literature, you can use it for interpretability, which is one of the reasons why someone might want to use these regime changes or detection methods. So because we want to maximize predictive performance, the regimes that are going to modify our beliefs, and I'll get into that in a little bit, may or may not be interpretable. The key idea is that as long as we capture a regime change, it's going to help us modify our model parameters so that we improve our predictions. So in that sense, as I said, our method seeks to unify and recover various methods across statistics, engineering, and machine learning. So for purposes of this talk, I'm going to focus on the one step ahead predictions in the streaming setting. So I'll start with that. So imagine we have a sequence of data points. Here I'm going to represent our features as X and our target variable as Y. And we're going to assume that condition on the feature X, there's some data generating process PF that we don't know, but YT is going to be sample from this environment condition on XT. So we get to see this sequence of data points, right? These pairs of XT and YT. We first observe XT, we make a forecast, then we get to observe YT, then we make a forecast with XT2, and then we keep going on and on and on. Now imagine we want to create a model that makes forecasts about some XT, some YT, sorry, given the XT. So we need two things. The first thing we need is a predictive model, right? This could be a linear Gaussian model. It could be your favorite neural network. It could be a time series model, whatever that is. But typically, if we have this predictive model, we typically want to approximate the posterior predictive distribution. And we're going to approximate it through some choice of predictive model. And it's going to be parameterized by some belief state BT. So the idea would be that once I make a prediction, then I'm going to update my beliefs from time t-1 to time t, having observed the new data point at time t+1. Sorry, this should have been dt. And this dt, just remember, is the pair of x and y's. So I make a forecast. To see how much error I did with that forecast, and then I'm going to update my beliefs based on that forecast. So if I were to plot the diagram of how that looks, so at time t-1, I make a forecast. With the beliefs that I have, I produce this y hat t, given my features xt, and then I update and I go along. Of course, here's where I make a forecast, but I'm not going to get to observe the true yt until I get to the next time step. And of course, each forecast is going to be the expected value under that belief state, given the data points that I've seen and the current feature at time t+1. So this is a very simple example of online learning, and this is nothing non-stationarity for now. So imagine that we have a Gaussian with unknown mean but known variance, and we have some prior, right? It's a classical problem. We have some prior over the mean. We're going to assume it's going to be Gaussian with M0 and S0 squared as prior. And then the posterior predictor is going to take this form, right? So it's going to be, the posterior predictor is going to be a normal. It's going to have some mean MT, and then there's going to be the variance, the addition of the posterior variance plus the observation variance. So I'm going to make forecast with this predictive model. Of course, the prediction is going to be always MT, right? Because it's going to be the expected value of this predictive model is going to be MT. And once I make a forecast, then I'm going to make an update. And this is the algorithm for the update, right? So first I'm going to make a forecast, and then the update at time t. is going to observe yt. So there are no features in this example. It takes this form, which, if you look at it, it's basically my previous mean estimate. My previous mean estimate plus some learning rate, but this learning rate is not constant. It depends on alpha t, and then the error that I incurred to forecast yt given mt minus 1, right? And this is going to be my posterior variance, and this is going to be my learning rate. But the point is that if you get to see this sequence of observations, there are indeed Gaussian with known variance and a known mean, then you get to see a bunch of data points, and then you converge in this well-specified scenario as a function of time. Then the posterior variance is going to converge to 0, and here in this case, the true mean, we converge to the true mean, which is here in this dashed orange line. So again, the point is to say, we're making a forecast, we see this sequence of observations, we make a forecast, we see how much error we did, and based on that error, then we update our beliefs over and over. For a more interesting example, we can do the exact same idea, but now for a linear autoregressive model. So suppose now that we have this target variable, y of t, it can be the hour ahead electricity forecast, given some past hour ahead electricity forecast. That's represented here by this feature vector a of t, which, as you see, is, okay, I want to estimate y of t given the features a of t, which are simply the past hour ahead forecast. And this is simply an linear autoregressive model. Again, for simplicity, I'm going to assume that I know the variance, but I do not know the coefficients, right? And because I do not know the coefficients, if we're being Bayesian, I can put a prior on that, and that's going to induce this posterior predictive model, which is simply a dot product between my previous mean estimate and the current features at time t, and this is simply the posterior variance, which is this sandwiched with the coefficients or the features, and again, my observation was variance. So that's going to be the model I'm going to make a prediction with. The prediction is going to be made with this term over here. So every time I'm going to make a prediction is with this term. And the update algorithm takes this form, which again resembles the one that I showed in the 1D example, just that now we're working with matrices. And now we're going to have this common gain term. But for all intents and purposes, this is really a learning rate or a learning matrix that is going to nudge all the model parameters mt minus 1 that is going to help us make predictions. Hopefully that makes sense. But of course, in these examples are well studied, and you can make updates, you can make forecasts at every time step, and then you can make updates. But the problem is when you come up with static updates, as we've seen. So at every time step, I'll make a new update, but we are currently in non-stationary environments. For instance, consider, for instance, this example where, again, we have I know the variance, but now the mean is changing over time. And in fact, this is sampled from a hidden Markov model, right? And condition on the regime, it's going to choose a different level, but the same mean. And imagine I simply run the algorithm that I showed at the very beginning, where you are updating your posterior mean, your posterior variance. Then you're assuming that there's no changes in the environment, so everything's fixed. And then, as we see, is that at the very first regime, it does adapt, but then over time stops adapting, and then, well, you see that it really doesn't capture any other estimates over here. So it wouldn't be a good model to make these forecasts, right? We might to use a hidden Markov model and then estimate the model parameters here. But algorithmically, what's happening here is that if you look at the equations, the posterior variance is tending to 0 as t tends to infinity. And this is a pathology that, even though it's nice to have these linear Gaussian models, if you assume that it's a constant variance or non-variance, then simply as a function of time, the posterior variance tends to 0, which means that the learning rate tends to 0, which means that there's no adaptiveness to it. Just to show you explicitly what I mean by that, is that if you look at this equation, this alpha t term is going to turn to 0 as t tends to infinity, and because this is 0 in the limit, your forecast at every time t is simply the one you had the previous time step. For a more real-world example, we can consider these forecasting encounters at the US-Mexico border, which I think has a it's quite illustrative on what you would expect for a time series model, right? Imagine that you already have a nice calibrated model up to 2009, and then you want to make forecasts with that, right? Imagine you already trained your model, you're trying to make like one step ahead. This is every month, by the way, so these are encounters at the US-Mexico border, and every data point is 1 month of data. So how many migrants you've seen at the border. And of course, this is from this Pew Research dataset, which actually government officials from the US do use to make these informed, hopefully, decisions about what to do. But imagine that we do want to make this one step ahead forecast, right? How many members, patrol units you send at the border. Ideally, we'd like to have a model. So if I have a model here, perhaps it's not going to work as well to forecast what's going to happen over here, right? So we should adapt the model parameters over time. But the question is, when do we adapt this model? Like, should we wait until we incur some errors? Or should we just know when we should update our model parameters? So again, I'm going to use the algorithm that I showed a while ago for the linear to regressive model. I'm going to make these forecasts, and after each forecast, I'm going to make an update, and then I'm going to plot the mean absolute error over time. And what we see is that, this is after normalization. We do see that, of course, as I get more information, I would expect the error to decrease over time, and it's exactly what we see. But then around 2014, it starts to go up again in error, following these static updates. Now, of course, you can say that it might be because we should use a different model, or because there was a regime change, or because some other reason. And this is exactly the point that I want to talk about, right? How do we create a model, at least for this very particular example, such that it is at least as good as this static model, which assumes that we have a fixed model, fixed set of parameters, and they don't change over time. So one thing you can do is you already have your predictive model. In this case, it's going to be my autoregressive model. I already have a set of beliefs that I want to update. I already have this algorithm. And I'm going to assume now that there's going to be an auxiliary variable that describes the regime structure. So this phi of t is going to be some variable that describes whether a regime did or didn't occur. And I'm going to assume that condition on this auxiliary variable, I'm going to modify my beliefs. And I'm going to see a little bit how that works. But the point is that now the setup that I'm going to be working with, consider this time series. So for now, I'm going to assume that I know the regimes. The regimes are going to be these phi of t values. So I get to observe first phi1, then I observe the feature, and then I observe the true value, right? The idea would be that if a regime change occurs here, then it would say, okay, a regime change has occurred. I want to be very precise on what it means in a little bit. But regime change has occurred, reset your model parameters so that when you make a prediction, it's probably uninformed, but it should have big standard deviation on the error. So this is going to be the setup that I'm going to be considering. And under this model, I'm going to assume that the y of t's are distributed according to this data generating process that I do not get to observe, but now are conditional on xt, the features, and some phi t, which is going to be the regime or the auxiliary variable. So how does it work? Now, imagine that we want to already have a belief on what it means to have a regime. And I'm going to assume that this regime lives in subset phi of t. Then having this auxiliary variable, then I want to create a predictive model that, if you notice, is not going to modify the model itself, but it's going to modify the belief state condition on this auxiliary variable. Having that, then I'm going to predict my beliefs. Now notice that I'm not going to use the update function that I defined, but a predict function that is going to modify my previous beliefs condition on phi of t. Now I'm writing it here in a very algorithmic way, but there was so the generalization in the description why this makes sense was introduced in this paper, again, from a signal processing paper. And in signal processing, you have this predict and then update state space model, where you first make a prediction of what you think is going to happen in a state space model, and then you make an update. So in this paper, it's introduced the general concept of a prediction of a state, but more than the state is the belief on that state, which is exactly what this wants to capture. And once you modify that belief, then you can make an update using the algorithm that you already had before. So what this slide wants to show is that this bit of information you already know. We already came up with a model. We already know how to update the model. Now we need two new components. We need a component for the regimes, whatever that is, and a model or an algorithm to modify our beliefs condition on this regime. So I'm going to show you a very simple example on how that looks. So first the diagram. So now, at time t minus 1, you get your belief at time t minus 1. Then you make a predict step. And then, so this will be between t minus 1 and time t. You get to observe phi t. With phi t, then you're going to modify your beliefs. Think my mean and my variance. And then I'm going to make a prediction condition on this phi t and the feature 6 of t. And then the process repeats over and over again. This is one example, for instance, of the 1D with Gaussian prior reset. So imagine we have a hidden Markov model. Imagine that we do not know that that it is a hidden Markov model, but for some reason we are given the fact that phi t takes values either 0 or 1. Imagine that 0 is that no change point has happened, and 1 is that a change point did happen. Again, like very algorithmic, just to come up with some ideas. But the point would be that in the predict step, what I'm going to do is, if there wasn't a regime change, so here phi of t equals 0, then I'm going to keep my previous posterior meaning. And if there was a regime change, then I'm going to reset that to some pre-specified mean and variance. So this is going to be the predict step, and then the update step is the same one that we saw before. But the point here is that the point of this phi of t is modify the predict step before observing any data, but knowing that something had changed in the environment, so that once we make an update, it reflects that better. So it makes use of the latest information. So this is how it looks like. So again, the same example with the hidden Markov model. We know, in this case, we do know when the regime changes happened. But all I'm saying is, once you get to serve these regime changes, then turn on set phi t to 1. So what's going to do algorithmically is going to reset to the prior mean and the prior variance. Of course, uncertainty is going to increase, and then it's going to decrease over time again, right? So we get to see here, we get to see here, we get to see here. Of course, the big assumption here is that you do know which is the value of phi t. You know exactly when it occurs. But assuming that you do know when phi t occurs, then in theory, you would get a much better model, hopefully, than the one that is static. So we can try it out. This is another example. For instance, imagine that you do know that you have k possible regimes. So this would be the algorithmic version of the hidden Markov model. So you get, instead of a belief that has one mean and one variance, now your belief state is a collection of means and a collection of variance, k of those, one for each regime. So in the predict step, all I'm going to do is keep the prior mean, keep the prior variance, and then just include the current regime, so that in the update step, all this is doing is that it's going to, so this is the learning rate. If it's 1, it means that something's going to get updated. If it's 0, it means that no regime gets updated. But at least one of them is going to be on, or just exactly 1. So what this is saying is that condition on the predict step, which has phi t, it gets to the update step, and the update is only going to update the regime that belongs to regime k. This is what this is saying. And this is how it looks like. Right, so here you don't want to forget any information. All you want to do is detect which regime there is. Well, we know where the regime change is, and what you're saying is, okay, which of the k possible beliefs am I going to update? Am I going to update the first, the second, or the third belief? Now here, I'm still assuming that I know where the regimes happened. How would that look for the time series example that I showed? Well, one use of the auxiliary variable could be, right, and this is up to interpretation. We start to create a model. It would be to say, okay, imagine that the auxiliary variable is the current sitting president in the United States, right? So, the value of phi t is the set of all presidents that have been in the United States. And I say, okay, imagine that I already have my model. It's a linear autoregressive model. I already have a way to update that, but now I want to modify my beliefs conditioned on there being a new sitting president. So, because this is a model and these are my regimes, I can decide what I want to do with my beliefs conditioned on these regimes. I could say, for instance, imagine that between any two regimes, I'm going to assume that the new president is not going to consider what the past one has done. So I'm just going to forget everything and start from scratch. Right? So I want to relearn a new set of parameters at every new regime. Would that work? So this is how the forecast would look like. So again, I know where the regimes happen here. I set them to be the set of all US presidents. It doesn't have to be, but in this model, I did choose that. So it makes forecasts. So here is 2008, and between 2008 and 2009, the forecasts are more or less quite good. And then a change point happened right over here. And by definition, so phi of t changed. So algorithmically, what I'm going to do is, again, reset my prior mean and my prior variance, not because I have to, but because that's how my model is acting. And we do see that the uncertainty is going to increase, right? Which is what we'd expect. We assume that new sitting president, new policies, so we have to start from scratch. And this is how it's going to look like over time. Now the question is, this is a model that is interpretable, but how good is it at making forecasts, right? So we have the static model, which is the one that I showed at the very beginning, and now we have this other model where you know where the change points happened. And you do see that at least between 2004 and 2009, it was much better, but it wasn't as good between 2009 and 2017. Right? And you can start arguing, well, it's probably because the policies didn't change much. But at this point, you don't know, right? You're already acting on that auxiliary variable. In fact, it's not good between 2009 to 2021, right? It was better that you just use a static model that knows the change points. So the takeaway from this example is that regime detection, it doesn't imply they're going to have a good forecaster, right? You could have a model that detects regimes. This is the regime of the sitting presidents, and acting on those regimes, you would hope to get a better model. That's why sometimes people want to use these regime detectors, but it's not necessarily the case you're going to get a better forecasting outcome. Unless you create one that does that, which is the next task. Now what happens if we don't know the regimes, right? Imagine that, now we have the predictive model. We have a way to update the beliefs for the predictive model. We have the auxiliary variable, and we do know what we're going to do if condition on the auxiliary variable, what's going to happen to the belief state, right? We already know that. But the next question is, okay, what happens if you do not know what's the value of this auxiliary variable? So in this case, you get to see a set of data points. You do not get to observe the phi of t's. It's still being generated by the environment, but you don't get to observe that sequence, right? You have to infer it from the data. So we're about to be Bayesian in a little bit. There should be unknown regimes above. You get to see the features and then the observations, features, target variable. We want to make these forecasts. And the question is, again, I already know how to make a forecast conditioned on phi t. And I already know how to update my beliefs, and I already know how to modify those beliefs. But how do I estimate the latent regime conditioned on the data? And that's going to be specified by a new update function. And it's going to be an update function that is going to parameterize the belief state, not for the next prediction, but for the best auxiliary variable. And as it turns out, how you define that auxiliary variable, for instance, it could be a discrete auxiliary variable. It could be, for instance, the time since the last change point, which, if anyone knows the Bayesian nline change point detection method, corresponds to that. But it could also be a continuous auxiliary random variable. Right? It could be the probability of a change point, which is discrete, or you could have no auxiliary variable. And then condition on that auxiliary variable, which is latent, and how you modify your beliefs based on the auxiliary variable, then you get to observe a bunch of methods in the literature, which is what we're going to call the bond framework, which is you already have an algorithm you already have a model to make predictions, an algorithm to update those beliefs. You have a model to modify the beliefs and condition on some auxiliary variable. But depending on which auxiliary variable, if you do inference over the auxiliary variable and over the beliefs of the model parameters, then you're going to get all of these methods in the literature. We have a bunch more, but I think they're some of the most significant ones on how you adapt to them. But the question now is, okay, we already know a way to update the beliefs of the observations. Now, how do we update the beliefs of this of the auxiliary variable, which is latent? So again, in sort of like our algorithmic way, the first thing we need is, again, the set of auxiliary variables, but now we're going to need a predictive model or a posterior over the auxiliary variables condition on the data set we've seen so far. Once you do that, then you're gonna, the one step ahead prediction is not going to be the predictive model condition on the features and the auxiliary variable, but it's going to be this weighted average over all possible auxiliary variables, right? Because you don't know exactly which is the best value for the auxiliary variables, then you need to infer it from the data, right? So we're about to see how it's going to be seen in a Bayesian way as doing inference over a state space model. But yeah, the point would be to say that you're going to make this one step ahead predictive distribution over the prediction over the next time step and the prediction over what's the best auxiliary variable. So once you have that, you have a predictive model for the auxiliary variable, you have a predictive model for the observations. Now you're going to update your beliefs. You're going to modify your beliefs with the predict function. You're going to update that the belief state given the new data point, and then you're going to update the auxiliary variable or the belief state of the auxiliary variable. And it so happens that if you put all these pieces together, then you start to recover lots of methods in the literature. And then you start to see that some people change, for instance, phi, and then they change this, and then they change this, and you compare it to another method that only, considers this, only one of these sets. So the idea would be to have like an algorithmic approach to how do we construct these methods. So the pipeline is a bit more tricky. It involves like a double for loop, but basically you're going to carry a subset of beliefs. With that belief, you're going to make a prediction, and you're going to do it for every single value of phi of t. Once you have this modified belief state, then you're going to update that belief condition on the data point. And once you do that, for all possible phi of t's, then you're going to update whatever means to update the belief states for the auxiliary variables over here. And again, the prediction is going to be the one step ahead forecast of your predictive model. These are some of the auxiliary variables that you can find in the literature. Typically, if you know what the regime is, such as sitting precedent, then you can just encode it in your model. But if you don't, you can use any of these auxiliary variables. For instance, the classical one would be the mixture of experts approach, which could recover mixture of experts approaches to make forecasts, but also the hidden Markov model, because you have k experts or k models, and you want to attack each of those. You have the run length. So here the run length is the time since the last change point, or how many time steps since the last change point. So this one is, like look back windows. Basically, you want to like train your model, and you have like a fixed set of k. This happens sometimes in finance, where you don't want to train your data from 1980s because it's stale. So you use a rolling window approach. A way to do that is through the run length approach, where you assume that the window varies over time. So you have to estimate from the data. But you can also assume that it's constant. You can also assume that you want to have a set of values that is either 0, 1, whether there is a change point or there wasn't a change point. You can take something continuous, for instance, or the probability whether there is a change point. Or you can always add more structure to what it means to have a regime. But the problem is going to be computational, right? So you can always have higher and higher hierarchies, but how you perform inference, it's really where it starts to become a bit complicated. But these are some of the ones we find in literature. But then how do we, so now we have a auxiliary variable, we have phi t, we fix it, and now we want to make inference over phi of t. We want to find a posterior. So what's going to be our belief state? A simple choice of a belief state will be to simply assign one weight to each possible value of phi, right? And the condition will be, well, each weight should be greater than or equal to 0. And of course, if we add all of the weights, it should be 1, right? We want it to be a probability mass function. A classical assumption that you're going to find in the literature is that you're going to get to assume that there's some state space model or some dynamics for the auxiliary variable that is conveniently chosen to be Markovian. Because if it's Markovian, then the posterior over the auxiliary variable given the belief state is simply going to be the weight for that auxiliary variable. And how you update this auxiliary variable weight is going to take this form, which comes again and again in the literature. But basically here is the predictive model. So the weight, the normalized weight for this auxiliary variable is simply going to be, just make a prediction with y of t, x t, and then modify it, use the predict function to modify bt. And then you're simply going to include all the possible information that comes from moving from the previous phi t minus 1 to the new phi t. In the case of the run length, would be to simply go from 1 to 2, from 2 to 3, because it's the time since the last change point. And you're going to weight that by the previous weight that you found at the previous time step, right? So it becomes a recursive formulation. And then you can just normalize that, and then you can get this form over here. Any questions so far? If not, I want to show you a concise example. So this is one choice of v of t, which is the run length. So again, I'm going to assume that phi of t is the time since the last change point. And because the time since the last change point, the process of phi of t conditioned on phi t minus 1 can be one of two. It can either increase over time. So this, for instance, it can go from 2 to 3, 3 to 4, 5 to 6, or it can go from 6 to 0, 1 to 0, 2 to 0, 3 to 0, or it can stay at 0, right? All we're saying is that if there was a change point, then it's going to be 0. And if there wasn't a change point, then I'm simply going to increase the count on when was the last time since the last change point. So we put this together with the previous equation that I showed and some of the other algorithms that I showed at the very beginning, then this would recover the Bayesian nline change point detection. So you would take this lambda, 1 minus lambda, you would put it here, and then you would recover the Bayesian nline change point detection method. And the only thing that you would need to specify would be to be this bit over here, because this one you know, it's going to be like a lambda, 1 minus lambda, and this one you already know, right? In the original paper, this one was chosen to be any member of the exponential family because of conjugacy properties. But here we're trying to generalize it to whatever predictive model you want. It could be as non-Bayesian as being a neural network, which makes a point estimate. And here the probability is a point mass over the weights. But yeah, this is the that's one example that you can recover with this framework. Another example is the streaming version of the hidden Markov model. So in this case, just for simplicity, I'm going to assume that the transition between any two regimes is known. It's going to be this matrix pi. Again, if you work out the math, it turns out that if you assume that the transition between one regime and the next is Markovian, then you get this form over here, which resembles the equation that I showed before. Just that instead here you do it for every possible k values. So you have two methods, right? They're all changing in the choice of how you update the belief for the auxiliary variable in the auxiliary variable, but you can fix the model that you use to make predictions and how you update those model parameters. And anyway, so the point is, if you put all these pieces together, so you have a predictive model, it can be, again, Bayesian model, or it can be a neural network, be whatever you want, that is parameterized by some belief P of t. You have some auxiliary variable which describes or represents changes in the environment. And then you get two update functions, one for the beliefs, for the observations, given the features, and one for your auxiliary variable, condition of the data set in the past beliefs. And you have some way to modify your beliefs. Then this gives us basically a vocabulary or a way to compare different methods in the literature. And at some point, yeah, so if you put all this together, then you get this bond framework. But one way in which you can think about this is that if you want to be fully Bayesian, making predictions within the bond framework, will be equivalent to if you have a well-specified observation model with a prior and a well-specified dynamics for the auxiliary variables that it's also Markovian. Inference that I showed before will be equivalent as doing inference in this state space model over here, where you see that the model parameters themselves can change over time. And these parameters are influenced by the auxiliary variables, but the auxiliary variables themselves can influence over the observations. And here you have the features at every time step. So at some point while writing this paper, I got very into, okay, how many methods can be fit into this framework? At some point, my supervisor just said to me, just knock it off. We need to finish the paper. But for the papers that I was looking, these are the ones that I found in the literature, basically. And again, you have tasks here. You can have, for instance, filtering, or you can have like segmentation and prediction. But people also use it for bandits, for online continual learning. If you see, like these are the more machine learning models, which can or cannot be compared to the previous methods. But the point of the paper is to say that, if you really change the target, instead of predicting images, you're predicting a signal. If you swap out that component, which will be the choice of your predicted model, choice of M1, then you can find a new combination of methods that you can just try it out for yourself. Just to give a sense of how we can use this framework, I decided to create a new method, which is the run length with variance reset. And so it turns out that if you compare all these methods, a good idea is to use the run length auxiliary variable, just because it's computationally it's very nice to work with. It's quite flexible to the hyperparameters, so it can be misspecified and still gives you nice predictions. But the problem with the Bayesian online change point detection is that as soon as it detects a new change point, you have to reset both the mean and the variance. But the problem is that, okay, as we saw before, right? If you detect a regime and probably shouldn't have, then you don't want to forget everything that you've learned. Now, this is very useful, for instance, if you're trying to use something like online continual learning, is that if you get into a new task, which may or may not be related to the previous task, you don't want to reset all your model parameters from scratch. So one thing you can do is just increase the variance so that the learning rate is bigger. And in that way, you don't have to forget, or you don't have to start from scratch. You simply use the models, right? Again, very algorithmically, as far as I know, there won't be any sort of state space model that would correspond to this. But the idea would be, well, you don't want to reset your mean because it's very valuable. And the uncertainty really just drives the learning rate. So we can create a method that exactly does that. And this is what I try to do with this method. So again, I'm going to consider so I'm going to show you how one could use this framework. First, as I said, we need to choose the predictive model. Here's going to be the autoregressive model that we saw before. With the auxiliary variable, the run length. Again, this is only the time step since the last change point. And the prior transition between any two regimes is that one, or whether there was or there wasn't a change point. So we already have the auxiliary variable and we have the predictive model. The next step is to modify the predict step. Now here, all I'm doing is the original BOCD method applied to this linear autoregressive model would reset both the mean and the variance if there was a change point. But here, because I want to keep the previous mean, because I don't know if it's going to help me or not, then all I'm going to do is simply reset the variance. Or I'm going to increase the uncertainty over the variance. Ideally, you would see that when you make a forecast and there was a regime change, the uncertainty is going to increase. But it should also help you to see that once you work out the math, and then you get to see the learning rate here, all it's going to do is that the learning rate is going to be bigger. And this is going to influence the mean more as a function of how much error you incurred. So that would be the idea for that one. And then we need to also update our beliefs for the auxiliary variable. And it takes this form over here. Again, it's the same one as the BOCD. So all I'm saying is, one could argue that this is the exact same BOCD method applied to this linear autoregressive model. But here I'm changing the predict step for the purposes of what I want to do, which is I don't want to forget valuable information that it's already coded in my model. So what happens? Well, okay, so if I deploy this model, here's the probability of the change point that is inferred from the data. We see that after a regime change of what we defined before to be simply the changes in sitting precedent, there is no regime change. And there's no regime change. In a clear way to see this is that the errors are good enough, right? And as long as the errors are good enough, then or mean-centered, then there's no need to activate a regime change, which is simply going to inflate the variance. But if at some point in time, for instance, we do get to see a regime change, and again, regime change here simply means there was a forecast that I did that doesn't conform with what I expected, then the probability of a change is going to shoot up. The original method would just reset everything from scratch. But here, all I'm doing is I'm going to make a prediction, and then I'm not going to algorithmically, I'm not going to care too much about that prediction because I'm going to inflate my variance. And then as you see, the uncertainty is more or less like concentrated here, and then it starts to make errors, and then it starts to concentrate again, right? Whereas previous methods, if I were to just deactivate the mean and the variance here, start from scratch, it would take a longer time to really capture that. Probably shouldn't have forgotten your previous mean and variance.
Just so you've got about 5 minutes.
Okay, yeah. Great. Okay, so this is how it looks like. So if I were to deploy this method, the run length, as it's called, the phi over t is this black line. This is the regime that the model detected. And we do see that it detects regimes actually outside when there was a change in the US sitting precedent, right? And again, these regimes may not be interpretable. In this case, this one, it does happen to be the point in time where what it means to have an encounter at the border does change. And then it means that it has to reset the model from scratch because the y hat has changed. So it has to do that here. But it's less clear on really what happened here, which was really within a sitting precedent. And compared to the known change points, this run length with variable reset, we see that it's the lowest incurrent error among the other methods. Now, of course, one can say, well, what happens if you reset also the mean? That will be the fairest comparison. And this is what happens, right? Which we see that, it's at the very end is better than knowing the change points or the change points that we set were the change points, and is better than static, but it's not as good as this run length with the variance reset for the model. And so I wanted to finish the talk by just showing some applications that we've been doing. So I just showed you one very simple time series example, but we've been applying this to also like online learning with neural networks in online continual learning for bandit problems and for infinite hidden Markov models and streaming reinforcement learning. So I wanted to just give you a quick overview of how this has been used. The first application when we first wrote this paper was for online continual learning. And the idea here is that you have this neural network. And again, this is a classical problem of, you want to separate class 1 from class 2. You have a neural network, but again, neural networks have lots of parameters. So if you were to just reset the model parameters, then you would need to retrain from scratch. So what we created this version called RLOUPR, which slowly resets the model parameters. And what we see is that it adapts much better, at least in this toy example, but also in other examples that we have, and it adapts quite well through time. So another example is contextual bandits. This is a paper that I'm currently working with people at the UMI. Another example is the infinite hidden Markov model, because sometimes you have a hidden Markov model, but you don't know how many regimes you have. So you might want to infer it from data. The problem with that is that they're very sensitive to outliers, so that you need to really think about, is this a new regime or is this just a spurious outlier? So how do you do a trade-off between, oh, this is a new regime versus this is just an outlier, and how do you calibrate those? We create a new method for that. That paper is under review at the moment, but the point is to say, this is something that we can get where you do have these regimes. This is the online infinite hidden Markov model, which was a paper that already existed, but then you get to see these like outliers over here, which may not necessarily belong to a new regime, and then you see that the predictions are very spiky, and this is our method over here. And then Finally, and this is still work in progress, but I want to show you in these applications on RL. Again, this is very preliminary results, but the idea here would be that you have this classical example in RL where you want an agent that goes from point A to point B, point A being the red box over here, and point B, this other red box over here. And then all of a sudden the regime changes, right? Or the goal changes, right? You want to go from this goal to this goal. So the agent has to adapt and then see, okay, how does it adapt its environment so that it gets as fast as possible to this other to the goal from the start. Yeah. So in conclusion, so I presented you the Bone framework. Again, the point is to say that there are a bunch of methods in the literature that can be recovered as instances for Bone from the ML community, but also from the stats community and the filtering community. So this unifies these methods, and we create a bunch of methods they're trying to be competitive and extensible. And yeah, thanks.